Yes, thank you very much for the kind introductions. Thank you for the opportunity for me to be here to tell you something today about higher derivative corrections. And I know I'm standing between you and your nice dinner, so I will try to make it as relaxing as I can do. Okay. And I'm very happy that actually Lorenz told you already how hard it is to calculate string amplitudes, so I don't have to press on this point very much. And here, you know, what I even want just to do is I want to calculate tree-level amplitudes, so Veneziano amplitude. And then you have seen already on his talk this nice expression here with a lot of gamma functions. And in principle, we can expand these gamma functions in terms of alpha prime, so which just describes the length of the string. So this is very well known. And you also know that we usually not use string amplitudes directly because they are so complicated, but that we rather use an low energy effective field theory. So that means we match these string amplitudes with some amplitudes in our supergravity theory. So, and what we are doing there in detail is actually first we are identifying the relevant degrees of freedom, so which here is just the metric, the B field and the dilaton, so the NS-NS sector to keep it as simple as possible. And then, you know, we also look at the symmetries. So here we have diffeomorphisms, of course, because we have a supergravity, and we also have abelian gauge transformations for our B field. And now in the next step, we just write down and for our action all the terms which are allowed by symmetry. So we have this very well-known building blocks and we just combine them in all possible orders. And in principle, we get the blueprint for our low energy effective action. Of course, you know that you could write down an infinite number of terms, so we have to find some parameter to expand in, and this is usually alpha prime, which just counts the derivatives. So this is, of course, what you all know, and in principle, after we have now matched with our string amplitudes, we get here our coefficients. But of course, you also know that there are certain problems in this procedure. And the first thing is that this number of terms which we can write down really explodes. So for example, when we would like to go to alpha prime to the power of 3, we had already 872 terms. And we would have to calculate a lot of amplitudes, which makes it actually not feasible to really go much higher. And then the next thing, of course, is connected to what we already heard in Lorenz's talk, so that there are also loop corrections, which we also would have to take into account. And at this point, you know, we get this whole plane here of corrections to supergravity. And normally, we really just work in this very, very small corner. So at the leading order in GS and in alpha prime. And of course, we have seen that there are some nice techniques using holography, for example, to explore these parts here of the diagram, or we could use supersymmetry, which protects some states to go in the middle here. But in principle, we do not know what happens there. And so this brings me to what I actually want to talk about today. I want to give a proposal of how we can actually get in here and how we can learn more about these corrections. And so the idea, what this all is based on, is actually we go back to the effective field theory. And of course, we cannot do very much with the degrees of freedom. But what we can do is we can look more at the symmetries we have. And so, for example, you all know that we also have fermionic symmetries, supersymmetries, for example. But it's also well known that when we have a lot of supersymmetry, it's actually very hard to deal with explicit supersymmetry. So that's why people were also exploring other routes, for example, hidden symmetries, which are also a very nice thing and very constraining. But of course, recently there were some no-go theorems for certain hidden symmetries that they will not be able to capture all higher derivative corrections. And so that's why today I want to propose an alternative route, which is more along the line of spontaneously broken symmetries. And of course, you know that spontaneously broken symmetries have a very, very successful history in physics. And in principle, there is a very nice recipe you can follow. So you can start actually with what is called the coset construction, where you have a group G of your full symmetry, and then you keep just a subgroup, so the residual symmetry H. And then by choosing your field based on a coset representative, you can actually write down again a candidate for a Lagrangian, and you can match it with amplitudes again, and you will get a low energy effective action. So this brings me now to my proposal, actually. So I want to propose to you that higher derivative corrections, and in particular alpha prime corrections in supergravity, they might be governed by some infinite dimensional symmetry group, which I now just call G Poincare infinity. And what I want to do for the rest of this talk is I want to show you what is this group and how does it work. So that means this brings me to the two natural questions in this context. What is this group? And so the guiding principle here will be that, of course, to get a larger group, we have to add something to our theory, but we will add it in such a way that we don't add any new unphysical degrees of freedom. And the second question is, of course, how do we use this extended group to get, for example, an action or the equations of motion? And you will actually see that this will be done by also a coset construction. And this coset construction will be done by generalized Cartan geometry. So that means the first point, we will use a BV formalism because so this is the way how we figure out physical degrees of freedom. And the second thing, as I already was mentioning, is done by Cartan geometry. And we will put both together. And then we have a recipe for finding out these higher derivative corrections. Okay, so let me give you an example because this is very, very abstract. Let's do something which we all know, and let's count degrees of freedom in linearized gravity. So this is one of the simple settings we can take. And so we start with a frame field here, so which actually will have just the small fluctuations around the identity. And then, you know, in gravity, of course, we have symmetries, we have diffeomorphisms here, and we also have Lorentz transformations because we just have a frame. And so at the linearized level, they affect the frame exactly this way here. So, and to keep track of all these kind of things, we put this in a little diagram. So we have our diffeomorphism parameter here, and we have our Lorentz parameter here, and they all interact with the frames through this linear maps here, the exterior derivative, and this map here, which I will call tau. Then we can do the same for the spin connection, which of course does not transform covariantly, but it's d, the Lorentz parameter. So we also put it in this nice diagram, and we have here again the exterior derivative. And so we go on, you know, we can write down the torsion, we look up the equations and linearize them. And again, we find that it depends on the frame and on the spin connection. And you see, so putting in the curvature, we actually get a nice diagram, and we can go on. We would get Bianchi identities here for the torsion and for the curvature and so on and so forth. So the nice thing about this thing is that it's actually a bicomplex, and what we do here, so this is a little bit technical, we also have to expand it with a Weil tensor, and I will explain in a second why. But you see, the most important part is that we have two maps. So we have D's going along this side here, and we have taus going diagonally, and then when we square the respective maps, we get 0. So that means d squared will give 0 as an exterior derivative, and the same for tau, for example, along this route here. And then eventually we can also go this route or this route, and it will give the same result. So this is what this identity here tells us. And then, you know, of course, I was promising you to find the degrees of freedom in linearized gravity. So how do I do this? I, of course, use my new gadget, this complex here. And in particularly, we will start always going diagonal here. So we will start at this point. And what we are doing is actually we are calculating the cohomology. So that means we are looking at this line and writing down here a chain complex. And you see we have here our Lorentz parameter, and here we have our frame. And the Lorentz parameter is, of course, antisymmetric in these two indices. So we just put two boxes above each other, and the frame can be in principle everything. So this is box times box, which of course decomposes into a antisymmetric and a symmetric part. But you see this antisymmetric part is killed by the Lorentz parameter, and so that's why we only keep the symmetric part. But of course, you all know that gravity has just a metric, and the metric is a symmetric tensor. So this is exactly why we have Lorentz transformations to remove this unphysical degrees of freedom from the frame. So when we do this again, so we will find that the cohomology here is trivial, and this is very good because we can fix the spin connection completely in terms of the torsion. And then we can do it again and calculating carefully the Bianchi identities and taking into account the Weil tensor, we get exactly the Einstein tensor here, which gives rise to the equations of motion for our metric. And then doing again this cohomology, we will find exactly the Bianchi identity, the contracted Bianchi identity, which we need. So that means going along this line here in linearized gravity, we really see completely what the theory is doing. So we are seeing gauge transformations here, diffeomorphisms, we are seeing degrees of freedom here. And then what we are doing is we are doing this trivial cohomology. We use it to fix the spin connection in terms of a derivative of the frame. And then we get the curvature or the equations of motion as another derivative of the frame. And finally, we get Bianchi identities. So this is how it works. So this is how we can identify degrees of freedom for linearized gravity. But of course, you might argue that linearized gravity is very boring. And we would like to rather do the full thing, full nonlinear gravity. And so there we can now use Cartan geometry. And I want to quickly show you how this works. The basic idea is actually to compress this chain complex, which we have just in one line, so to unify it. And so what we are doing is we are looking first here at our diffeomorphism parameter and our Lorentz parameter, and we can actually unify them into a Lie algebra valued element where we just take translation generators, pairing them with the diffeomorphism parameter and Lorentz transformations, of course, with the Lorentz parameter. And so that's why we get one unified object here. And we do the same here for the frame and for the spin connection here. Again, translations and Lorentz transformations. And the same can be done for the torsion, the curvature, and also for all Bianchi identities. And so this way we take all what we have here just in one single line. And for the moment, we don't care really very much about the Weil tensor. When you are interested in this, I can tell you later on more about it. But so then the last thing we have to do is we also have to unify these maps, d and tau. And so what we can do is actually we can write them in terms of what people call a Cartan connection. And this is really like your normal gauge connection in a gauge theory, d plus, and then you have a connection one form here, which you wedge with. And this Cartan connection actually includes the frame and also the spin connection. And now the nice thing is we can really use the full frame here, the full nonlinear frame, and we will still get this nice complex which we started with. So this is what we are doing, and there is now a very nice interpretation here, because you see that we started with Poincare, but then we were eliminating the Lorentz transformation. So that means we are working on the coset Poincare mod out Lorentz transformation. And of course, you know that this is just flat Minkowski space, which we use here as a tangent space on this point. So what we are doing is we are doing a coset construction on every point of the manifold. And this is exactly what Cartan geometry is doing. So now I have shown you how you get Poincare in gravity, but of course this is something what you know, and I promised you something else. I promised you Poincare infinity, right, which is much more fancy. So how do you get this one? And to get this one, the only thing you really have to keep in mind is that the string is an extended object. So it will not couple like an electron, for example, to a one-form field, but it will couple to a two-form, the B field. And then, of course, this two-form has a three-form field strength. So why is this so important? This is so important because when we look at transformations of this two-form, so we see that it has a D of a one-form and it has diffeomorphisms. But so because this is a one form and not a zero form, we can take this one form as D of a scalar. And so we have a transformation which will still not change the B field. So this is the notion of a trivial gauge transformation or gauge for gauge transformation. And this thing we have to take into account when we now try to write down the same complex which we wrote for normal gravity for the string. And so we not just start with the parameter for the gauge transformation, but we also have this gauge for gauge here. And then in principle, you know, we can now try to write down all these other spaces by now taking into account that we not just have one box here for diffeomorphisms, but also one box, additional box for B-field gauge transformations, because so these are one-form gauge transformations. And then, of course, we need to know all these spaces. But here again, Cartan geometry helps us. And it's, of course, not normal Cartan geometry, because now we also geometrize this gauge transformations for the B field. So that means we have generalized Cartan geometry. And at the moment, please just take generalized Cartan geometry as a black box. And the only thing what it's doing is that I know these representations or these vector spaces here, and it will tell me what I have to put here. So, and I will explain you in a second a little bit more how this works, but for the moment, this is all we need to know. So, and what we are doing now is, so we are just going along this line, and here we have to again put our degrees of freedom. And so our physical degrees of freedom are just the metric, the B field, and then the dilaton, so the one from the second slide. And then when we do the cohomology again, we see that we not just get one Lorentz transformation, but we get actually also a second Lorentz transformation. So this is what's called double Lorentz transformation. And this is, of course, a standard feature of the closed string, right? Because we have a left moving and a right moving sector. So this is still fine. The really interesting thing, which is different from normal gravity, happens now. Because when we now look at the torsion here, we will find that it's not sufficient to fix the spin connection on its own. So this is a very well-known problem, so that the spin connection has more components than can be fixed by the torsion. And the solution, so I would like to propose, is actually to use a new symmetry, some kind of a Stückelberg-like symmetry, which actually gauges these components which you cannot fix. And so you get this additional gauge symmetry, and then you can complete your cohomology, and actually you can get a trivial cohomology here. So, and then you go further on, you know, so you now get some additional spin connection for this new symmetry here, and you also get a spin connection here for your gauge for gauge symmetry. So this is special and generalized Cartan, but in principle, you can go on and do the same cohomology here. We want to just keep our standard equations of motion. And when we do this again, we get some additional representations, and these will actually furnish Poincare infinity. So here you see this part here, and this part would be normal Poincare, translations, and Lorentz rotations, and now you get two copies of it, and it goes on for infinity. So this is the idea here, and for a second I just have to tell you what is this mysterious generalized Cartan geometry, and I don't have very much time, and we want to go to the dinner, so that's why I just tell you this always arises when you have gauge for gauge symmetries like this one here, and then you also have to add additional connections for this gauge for gauge series. So the thing here I call rho, and then they come with curvatures and so on and so on and so forth. And for the experts among you, so this actually follows what people call the tensor hierarchy. And then what you get is, so you get this kind of nice new model space. So now in generalized Cartan geometry, a coset is actually G mod out H twiddle. So you get a double coset, and the double coset will actually describe your generalized tangent space, which is normal tangent space for diffeomorphisms, and then you have a cotangent space for B-field gauge transformations. And what we have achieved by this cohomology discussion, we have just fixed this part here. So for normal Cartan geometry, this would be all, but now we also have here another Lie group, H, and this one is not fixed yet. But what we can do is we can actually use the fact that this together has to form a Lie group on its own. So that means these generators here are tightly constrained, and we can actually fix them completely when we just define a bilinear form on them, which can be used to reflect what we already know from here to here. So let me quickly show how you get corrections from these prescriptions, how you get higher derivative corrections. So what we are doing is actually we first take into account that we now know that these things are in the Lie algebra, and this new Lie algebra we have seen for H. So we can just write them as Lie algebra valued, and the diagram looks already a little bit nicer. And then what we are doing is we are doing this zigzagging procedure. So that means here we have our frame, and then we have our trivial cohomology, so we can express our spin connection in terms of one derivative of our frame. And then we can go on again. So, and we now can express these higher connections with two derivatives of the frame. And this goes on and on and on here. And you see when you go down here, the number of derivative grows. So that means this will automatically give you alpha prime corrections here. And of course, an infinite number of them. And then the question is, how do these alpha prime corrections land up here? And this is actually, when you look at the linearized level, you will not see it. But at the nonlinear level, you will see that you have a commutator between two of these connections. And then you just have to remember what this Lie algebra H is. So when this kappa here, which controls this Lie algebra, vanishes, it is just a graded Lie algebra. So that means to land here, we have to have a 0 here and a 0 here. So that means we will don't have any alpha prime corrections, but when the kappa is non-zero, we will get a filtration. So, and all these higher correction terms will land in our equations of motion, and we get a tower, an infinite tower of higher derivative corrections. Okay, let me quickly now say how this relates to the literature. So the only thing which we now need to know is this kappa here, and we in principle can parameterize it now. We have to check which of these kappas are admissible. And we, for example, know very certainly that we have at least two different choices of this kappa, one for the left moving sector and one for the right moving sector. And we also have seen, so this is work in progress, but it's very likely that there are even some more, so some like C and D. And now we can check what this really means. So this will always give you different towers of higher derivative corrections. And the first one we have identified with the known results from the literature. So this actually gives rise to what people know as the generalized Birkhoff-Durot identification. And so far, this was just calculated to alpha prime square. But with our result, we can write down all order results. So we can really write down transformations to all orders here in alpha prime. And then these two new parameters here, they will give rise to a new tower, which starts at alpha prime to the cube. And this is exactly the one you need to capture the theta-3 transformations. So, and this is very nice because it circumvents a no-go theorem for this alpha prime to the power of 3 tower that you cannot obtain it just from a hidden symmetry. But of course, we not just need this hidden symmetry, we have an infinite dimensional symmetry. Okay, so let me finish. So what I want to just quickly recap. So I told you a little bit about field theories, symmetries, and geometry. What I did not tell you because I did not have time, so what I was doing now was only string-based, but the whole lot of technology we are using can actually also be done for membranes. And we have now a generalized Cartan geometry for membranes where just here the full tensor hierarchy of the membranes arises and we get more and more corrections. And so this is very interesting because we could probably even do GS corrections. I mean, this is what we are trying to do. And another nice aspect is that we can also have different realizations of these algebraic structures, and this will give rise to dualities in string theory. So there are a lot of possibilities. And here I just want to stop and thank you very much for your attention.
So you started saying something about string as matrix.
The scattering. Yeah.
Yes, and that encodes all information about this effective action, say bosonic string theory. So normally we are used to this idea that if there is some symmetry which is really relevant, not these cohomologies, not gauge ghost for ghost, etc., physical symmetry, it should be encoded in this matrix.
Yes.
So do you have any suggestion?
Yes. This is a very good question. I mean, so what I was now doing is it was just the target space perspective, but when you would do it on the world sheet, so what I'm claiming is that the number of counter terms you can add to your action is very, very much restricted. And there is some symmetry which really restricts the amount of counter terms which you can write down. And to give you an example, so just very, very quickly, yeah, let me show it to you here. So here you see it. So at alpha prime to the power of 3, I was telling you in principle you can write down 872 counter terms, already mod out by field redefinitions. And what I'm telling you with this symmetry, you can actually just write down 4 counter terms. Exactly. What these constants are, I mean, the funny thing with these constants is you have a Z2 symmetry, left and right. So that means they will be fixed differently for bosonic, heterotic, and type 2. And then here you will find for this concept something proportional to zeta 3. So this you still have to calculate from the string scattering. I mean, it does not know about these values of the constants. It just tells you you have much, much less to calculate because there is an internal symmetry. Okay. Thank you. Thank you.